Okay, so without looking at your notes, who remembers what we're talking about in this class?
Body mechanics.
That's true. Can anyone be more specific than that?
We weren't allowed to use internal loads.
Distributed forces.
Yeah, okay, so internal loads, internal loads with distributed loads. Kenny's gradually doing, he doesn't like to do the daylight savings all at once. He does it gradually over the week.
Give me about a minute.
Yeah. Once in college, I tried to save my hour until finals week, but it was a really half-baked idea that really didn't go anywhere. No, I don't condone that. We'll talk about that after the video is off. Okay, so, and I said this in dynamics too. So on Friday before break, I posted an assignment. There's a bunch of problems on there. That's going to be most of the problems that you're going to be responsible for the quiz this week. So if I add any other questions, there won't be very many. It'll be mostly the stuff that's already posted. Okay, so we've been talking about internal loads. Last time we talked about how to do internal loads when you had distributed loads. And so I'm going to start out with an example, but first I want to point out one thing that's really useful as a check on your answers. So the 6 checks on internal loads answers. The first one is that at any point on the beam, the x derivative of the bending moment has to be equal to the shear force. The second check is at any point the x derivative of the shear force has to be equal to negative q where q of x is a downward distributed load function. The third check is that the bending moment is equal to 0 at an endpoint if and only if there's no point couple at that endpoint. Three, 4, and 5 are kind of similar. It's the same idea with first bending moment, then shear force, and then, oh no, we have 6 left. So 3, 4, 5, and 6 are all basically the same. Bending moment, tension, shear force, and torque. So 4 says the tension at an endpoint is equal to 0 if and only if there's no horizontal point force at that endpoint. Five, the same thing for shear force. So shear force is equal to 0 at an endpoint if and only if there's no vertical point force at that endpoint. And the last one, the torque is equal to 0 at an endpoint if and only if there's no point torque at that endpoint. Okay, so let's go through an example, and after we get the answer, we'll do these 6 checks. Okay, so let's say we have a beam connected to the ground at a pin on the right end and supported by a roller at its midpoint. And let's say that there is a horizontal point force of 1,000 newtons at the midpoint. And then let's say there's these 2 sort of lever arms. So what's going to be happening here is there's going to be a force pushing this way into the page and on top pulling out of the page. It's going to have the effect of torquing that endpoint. And both of these are 800 newtons. And one of these moment arms, let's say, is 0.07 meters. The weight of this beam is 300 newtons. What are the internal loads? Yeah, 0.2. So this is at the midpoint, so each one of these is 0.1 meters. Okay, so the first thing we have to do is figure out how to represent these external loads. I'm just going to, draw a free body diagram of the whole thing. I'm going to replace, so these are 2 equal and opposite forces pointing in opposite directions. Well, that's the opposite part. 2 equal and opposite forces, 800 newtons. So that's a couple. And we usually represent couples as just a point moment. So the question is, what's the direction of the moment of that couple? That was your left hand. There's no left hand rule in this class. Yeah, right. That's the way to do it. Just right hand rule. Okay, so it's going to rotate this way. So your thumb's going that way. So it's down the length of the.
What are the symbols for the X and the?
Oh, yeah, right. So the one with the dot in the middle, it's like you're looking at the point of the arrow. And the one with the X, it's like you're looking at the feathers of the arrow. So, never seen that before. That's amazing. In my classes, so it's a. It's not really that he hasn't seen him. It's this he hasn't been paying attention at the time that he's seen it. Okay, so that couple goes like this. And what's the magnitude of that moment? 56 or 5.6? 56? I'm going with 56.
Why wouldn't it be double that? Because you have one lever arm going one way and the other one's adding to it.
Because let's think of it as, okay, you asked for it. I'm not going to go through that whole derivation. That's what I thought I was going to do for a second. But let's just think of it as like pancake table for that couple. So what's the moment of that couple? Pancake, artist, row, 4, marzipan. So the x-axis, we're going to use a coordinate system like this with the x-axis going right down the center. And so the upper 800 Newton force is at the point 0, positive 0.070. We'll make the about point at the origin. So subtract, and you get this for a row vector. What's the force? The top one? Positive z, yep. 0, 0, 800. Oh, yeah, it should be twice that. Yeah, it should be. Okay, well, let's finish calculating it. I'm glad you mentioned that. So that's 56, 0, 0. And then the bottom 800 Newton force is at 0, negative 0.070. So the row vector is 0, negative 0.07. The force is 0, 0, negative 800. And so you get a cross product again of 56, 0, 0. And so the total moment is 112, 0, 0. Okay, so now let's do a free body diagram of the whole thing. So it's pointing this direction, 112. And what else do we have? We have this point force of 1,000 newtons. And now that we've chosen the body to isolate, we can represent the weight force as a point force. So that's 300 newtons down, acting at the center. And then the reaction forces, there's one here from the roller. I'll call that RA. And there's one here from the pin joint with an unknown direction. Call that RB. Any questions about that? Okay, so Newton's second law says 0 RA plus 0 negative 300 plus RBX RBY. When I almost missed the thousand, so negative 1,000 0 is equal to zeros. And the moment equation about the z-axis, and let's put the about point at B, says, well, that RB doesn't produce any moment because it's acting at the point B. The 1,000 doesn't produce any moment because its line of action is through B. 300, that has a moment arm of 0.1. And would that cause a positive counterclockwise or clockwise rotation around B? Yep, so that's positive. And then same moment arm for RA, but that one would be clockwise, so minus 0.1 RA is equal to 0. And then the rotational equation about the x-axis, and I guess the point that we want that axis to go through is the center of the beam. Okay, so what do we have on here that would produce, I forgot one thing on the free body diagram. This pin also would resist rotation about the x-axis. So that's going to produce an unknown reaction torque, fancy T. So this free body diagram needs to have this.
What is the 10,000 and the negative x for?
That was just an applied force that was given in the problem. That's just saying that something is pushing on it right at that point. Yep. So like maybe there are two extensions coming out towards us and away from us, and something's pushing on those. Okay, so we have positive 112 plus fancy T is equal to 0. And so RA is equal to 300. RB is equal to positive 1,000, 0. And fancy T is equal to negative 112. Newtons, this is Newton meters. Okay, so now we can go to the cuts. Any questions yet? Okay, how many cuts do we need? Yeah, there are 3 points where these subfunctions are going to change, the two endpoints and then that middle point, so we need two cuts. So cut 1 is valid for x's between 0 and 0.1. There's a torque of 112. We haven't, so the right end is before we get to this stuff at the middle. The only other thing acting is the weight, and so we need, well, besides the internal loads, so we need a way to represent the weight. And remember, the weight is a distributed load. You can't treat it as a point force until you've chosen the body to isolate. So what's the distributed load that represents the weight? How do you calculate that? That's right. So it's the entire weight divided by the entire length. So 300 divided by 0.2 is, what's that, 1,500? So that's 1,500 newtons per meter. And then we have the internal loads: tension, shear force, bending moment, and internal torque, fancy T. And now that we've chosen the body to isolate, we know that our body is x meters long. We can rewrite this with the weight represented as a point force. So that's 112. What's the point force? What's the weight as a point force? You have 1,500x. And then we have the internal loads: T, V, M, fancy T. Okay, so Newton's second law says 0, negative 1,500x plus T, negative V is equal to zeros. So T is equal to 0. And V is equal to negative 1,500x. And now the moment equation about the z-axis. That torque 112 isn't going to produce any moment about z, but this will. And our about point is always on the left. Okay, so what's the moment arm of that 1,500x force? Yeah, so x over 2 times 1,500x, and would that cause a clockwise or counterclockwise rotation? Clockwise. And then we have plus m minus vx is equal to 0. So m is equal to vx plus 750x squared. So that's negative 1,500x squared plus 750x squared gives you negative 750x squared. And then the torque, so the moment equation about the x-axis. We have positive 112 plus that internal torque is equal to 0. So the internal torque for this region is equal to negative 112. And these subfunctions are all valid on the interval between 0 and 0.1.
What happened to the 1500x for the moment?
Oh, okay. I skipped a step here. So this one is x over 2 times 1500x gives you 750. X squared goes the other side, but then you're adding that to vx. Vx is minus 1500x squared, and so they half cancel. Okay, cut 2. So x is between 0.1 and 0.2. So we have the distributed load representing the weight, and that's still 1,500, what was it, 1,500 newtons per meter. We still have this external torque of 112 on the left. And now we're going to include these point loads that are acting at the midpoint. So we have RA of 300. We have a horizontal force of 1,000. And then the internal loads T, V, M, and fancy T. Yep.
Oh, never mind. I was going to ask that 1,000 used to be on the top, but I guess it really doesn't.
Yeah, it doesn't matter. I'm just putting it wherever it seems to clutter things the least. Okay, so now we can represent the weight as a point force. It's going to be the same thing it was before, 1,500 x acting at a distance of x over 2 from the left endpoint. And there's the 1,000. And there's the 300. And then we have our internal loads, T, V, M, and torque. Any questions about that one? So Newton's second law says 0, negative 1,500x plus negative 1,000, 0, plus 0, 300, plus T negative V is equal to zeros. So T is equal to 1,000. V is equal to negative 1,500x plus 300. And now the moment equation about the z-axis, and our about point, like always, is at the left end point. the moment arm of that 1500x is x over 2. And that's counterclockwise. No, it's not. It's clockwise, so that's negative. What's the moment produced by the 1,000 Newton force? 0. What's the moment arm of the 300 Newton force?
1.
That's right. That's a fixed amount because the location where that 300 Newton force is applied doesn't change as you move that right endpoint around. It's stuck there, 0.1 meters from the left endpoint. Okay, so no matter where you, so look back at the original picture. No matter where you, say you did a cut there, how far is that 300 Newton force from the left endpoint? It's 0.1. Now what if instead your x was this much and you did this cut? How far is the 300 from the left endpoint? 0.1. So it's not going to depend on x. All right, so 0.1 times 300, and is that clockwise or counterclockwise? Counter. And then we have plus m minus vx is equal to 0. So m is equal to positive 750x squared minus 30 plus vx. So that's 750x squared minus 30 minus 1500x squared plus 300x. And you can simplify that a little bit. And you get that m is equal to negative 750x squared plus 300x minus 30. And then the last one, the moment equation about the x-axis. We have the same stuff we did before. We just have this 112 Newton meter torque and then the internal torque T. So we have 112 plus fancy T is equal to 0, and so you get fancy T is equal to negative 112. And all these are valid on the interval from 0.1 to 0.2. Okay, so now we're going to do those 6 checks. So the first one is at every point, dm dx has to be equal to v. So that has to be true on that first interval and on the second interval. On the first interval, dm dx is equal to v, so that works. Okay? Just the x derivative of negative 750x squared is equal to negative 1500x, so that works. On the second interval, take the derivative of this. You get negative 1500x plus 300. That's equal to v, so that one works. The second one says that at every point, dv dx is equal to negative q. Okay, so on the first interval, take dv dx, you get negative 1,500. Take the negative of negative 1,500, you get positive 1,500, and that's the downward distributed load. Right? The downward distributed load was positive 1,500 newtons per meter. Okay. On the second interval, you get the same thing. I don't think it changes at all. Well, it does a little bit. So dv dx is equal to negative 1,500. Take the negative of that, you get positive 1,500, and that's the distributed load. Okay, so that one works. And then you could say, well, I did it in a different order, but let's do the check on when the internal tension is equal to 0. So the rule is the tension at an endpoint is equal to 0 if and only if there's no horizontal point force at that endpoint. So is there any horizontal point force at this endpoint? No, there's a couple, but not a horizontal force. So we know that T should be 0 here. Okay? Is there, well, let's do that one first. So if we're looking at the left endpoint, what's the relevant subfunction to use? Do we want to look at cut 1 or cut 2? Cut 1 is the one that represents all these points, so it doesn't make any sense to use the subfunction representing cut 2. Okay, so, and we get that T is equal to 0 over that whole cut 1. So that condition is met. Who follows what I'm doing? Okay, good. Now let's do the shear force one. Shear force is equal to 0 if and only if what? At an endpoint. Yeah, so at an endpoint, shear force is equal to 0 if and only if there's no vertical point force at that endpoint. So, oh, I didn't do the, sorry, I only did half of this. Let's go back to tension for a second. RB, there is a horizontal point force at the right endpoint, right? And so there should, so the internal tension should be non-zero at the right endpoint. And do we get that? Yeah, if we go to that second cut, we get that the internal tension at the right endpoint is equal to 1,000. It's non-zero, so that works. Okay, so now go to V. Is there a vertical point force at the left endpoint? No. So we expect the shear force to be 0 at the left endpoint. Is there a vertical point force at the right endpoint? There could have been, but it turns out that there wasn't, because just the way the math worked out. And so we should get 0 for the shear force at the left and the right. Okay, so at the left, plug 0 in for x, and you get v equal to 0. So that works. And at the right, plug 0.2 in for x, and what do you get there? You get 0. And then fifth, the bending moment is equal to 0 at an endpoint if and only if there's no point couple at the endpoint about the z-axis. Okay, so is there a point couple at the left endpoint about z? No. At the right endpoint? No. So we should get 0 for m at the left and the right. So at the left, go to that first cut, plug 0 in for m, and you get or 0 in for x, and you get 0 for m, so that works. The second cut, m should be equal to 0 when x is equal to 0.2. So what do you get when you plug 0.2 in there? Hopefully you get 0. Okay. So that one works. We have one more to go. The internal torque is equal to 0 at an endpoint if and only if there's no point torque at that endpoint. Is there a point torque at the left endpoint? Yes. Is there one at the right endpoint? Yep. So those should both be non-zero. And we get negative 112 at the left endpoint and negative 112 at the right endpoint. Any questions about that?
Will we have problems where we have a distributed torque or torque as a function of x?
No. That I suppose could be possible, but we won't do any like that. Any other questions about these? Okay, so there's so many places where something can go wrong in doing these calculations. It's sort of nice to have these checks at the end. Also, something that might occur to you as you start doing a lot of these problems is like you'll get done calculating, like say you get done calculating your shear force from Newton's second law, and you start to go into calculating the moments, which is the more tedious part, and you think like, wait a second, why don't I just integrate this if we have this relationship, you know? And you know what I'm saying? The problem is you're correct in that thinking, except that you'd have to deal with that constant of integration. And there are ways to figure out what the constants of integration are, but they're at least as tedious as just going through the moment equation. And so it doesn't save you any time or effort. But once you know the shear force, if you have values that let you calculate those constants of integration, you could calculate the bending moment directly from that. Same with if you have the distributed load, you could calculate the shear force directly from that. Okay. So now, combining internal loads with structures. So, for example, let's say that you have this structure. Where each of these is half a meter. This end, let's say, is connected back to the structure, and this angle is 30 degrees. And let's say we know this distance, it's 1 meter. And then there's a 1,000 Newton point force acting like that. What are the internal loads in each of these two members? Okay. Okay, so can we do this kind of problem? Yeah, we can do it. We can do this as long as there are no distributed loads including the weight in non-horizontal members. So if I added a weight to this diagonal member, then we wouldn't be able to do this. In statics, we actually did those problems, but we're not going to do them again in this class. But so the people who took statics with me, you can feel a little superior about that. Unless you don't even remember doing that, then it doesn't help that we covered it. Okay, so what you have to do you have to re-express the loads in the non-horizontal members in a coordinate system with the x-axis along the beam's long axis. So, for example, when we solve the structure, we're going to have a force, in this coordinate system. And then we'll have this and this. And we want to re-express it in a coordinate system like this. So we'll still have this t, we'll still have this 1,000, but the components of this now are this way. Okay, and then once you do that, this is equivalent to the way we've been doing beams all along, where we have that, and that. Okay. So if only we had a way to represent vectors in a new rotated coordinate system. So I guess that's it. Have a good summer, everybody. No, okay, so what we're gonna do is point force by point force. We're gonna multiply these by a rotation matrix to express them in a new coordinate system, and then we'll be able to do these problems. So I'll do an example of that next time. Okay.